Let's spend some time on an exercise. Here is a partial definition of the EQ type class, which you will need for the exercise, and here is a custom type called myBool, and it is your task to define an instance of EQ for the myBool type class. Since the EQ type class is a bit different and defines operators which are supposed to be used in the infix position in between arguments, here is an example partial implementation showing how you can define one of the entries of the equals function. Pause the video for a moment and try it yourself, then I will go through the solution with you. Well, how did you get on? Here is the implementation which I have written. The definition for the equals function is as you would expect. We just go through each combination of values and return either true or false, depending on whether the values are the same. For the not equals function, we take a shortcut and just call the equals function and then call not to turn it into the opposite. This leads us on to our next topic, default implementations. You can actually provide default implementations of functions when declaring a type class. And if we look at the rest of the definition of the EQ type class, we can see it in action. Here, we can see that not equals has a default implementation defined in terms of equals, and equals has a default implementation defined in terms of not equals. What that means is, when we go ahead and define our instance, we do not necessarily have to define a function implementation. We can just rely on the default implementation in the type class declaration itself. If we go ahead and define a function implementation, then our definition will override the default implementation. In this case, since the default implementations of the EQ type class are mutually dependent, we need to at least provide a custom implementation for one of the functions. And so only one explicit function implementation is actually needed. Since they are mutually dependent, if we don't override at least one of the functions, then we will get a warning when we try to compile. And then, if we try to use the default implementation, equals calls not equals, and not equals calls equals, in a loop until the program blows up and throws an exception. So we have to make sure to override at least one of the function definitions to avoid this. Default implementations are useful, and when you can define them, they can save you time, which otherwise would be spent repeating function definitions throughout multiple instance declarations. Defining instances for EQ for your types can quickly become cumbersome and annoying. In this case, the definition of the myBool type is simple, and so is the definition of the EQ instance for it, but you can imagine how a type which has 5 to 6 fields can quickly become unwieldy to write EQ instance declarations for. Also, the type of code you are writing is essentially boilerplate code. To check for equality, you just need to pattern match on each possible outcome and return true or false if they are equal or not equal. And so Haskell offers us a better way. We can actually ask the compiler to automatically derive instances of type classes for our custom types by adding a deriving clause to our type declarations. Here is an example where we are defining a type called myBool2. We add the deriving clause to the end of the declaration and instruct the compiler to generate instances for our type for the show and EQ type classes. And so now we can use the show and equals functions without having to write any specific implementation. The only classes in the prelude for which you can derive instances for are EQ, odd, enum, bounded, show, and read. Now if you remember, in one of the previous modules, when we were just starting with Haskell, I mentioned that you should just take a leap of faith and add deriving show to all of your type declarations to avoid getting an error such as this. This error occurs when we try to see something in GHCI, in this case some parameter, d1, which does not define an instance of show, and so GHCI does not know how to print it to the screen. The error message says, no instance for show day, meaning the type day does not define an instance for show. The way we fixed this issue was by adding the deriving show clause to the type declaration for the day type. Then everything worked. Now we have come full circle and you can understand exactly what is happening. The deriving show clause is instructing the compiler to automatically derive an instance for the show type class for the day type. That way you don't have to write one yourself. And the instance of show defines a function which can take a value of type day and convert it to a string, which can then be printed on the screen by GHCI. It took a while, and I promised I would explain what was going on, and finally we have got there. Deriving type class instances for EQ and show is extremely common for your custom type definitions and is a very handy feature that saves us having to write tons of boilerplate code. This video is a clip from a longer video for beginners starting with Haskell. Check that out if you would like to see all of the content. Also check out the entire Introduction to Functional Programming with Haskell course on the Learn channel. See you next time.